The next section of the integration chapter is differential equations. The idea behind a differential equation is essentially an equation which involves a derivative. So what we might be used to with an equation that has x's and y's, perhaps we rearrange or we use that equation to represent a curve. Well, now we have equations that might also involve dy by dx, the derivative of y with respect to x. There are all sorts of different types of these. We're going to focus on differential equations which are linear to start with, which means there won't be any second derivatives, d2y by dx squared, or any of those. You've already seen differential equations in some sense, but we haven't thought of them or talked about them as such. This is an example of a differential equation. If you were given this and asked to find y in terms of x, essentially what you're doing is solving the differential equation. You would probably think we already have the gradient function, so to reverse it we integrate with respect to x, and that's exactly right. It might be helpful to think more carefully about what that looks like on the left hand side as well as the right hand side, because it's easy to think of dy by dx as being the gradient function is, followed by y equals, as in now I've integrated, I have the original function. But if we think in terms of doing the same thing to both sides, like we would with an ordinary equation, then it can help to give us a clearer idea of what's going on and avoid some common pitfalls that you can fall into. So the first thing to notice here, which will be different to the type of differential equations we'll look at in a moment, is that the only time y appears is in the form of dy by dx. So there are no y terms, there are only the first derivative of y, dy by dx. Everything else is a function of x. That's what makes this particular form a bit more straightforward. You can essentially treat it as an integration question directly. And this is how we do it. Now if you look closely, we're integrating both sides with respect to x, which means that on the right we have what we would expect, the integral of that stuff. It might look messy, but each of those terms is a term that you can integrate directly without any fancy trickery, parts, any of those things. On the left hand side we have the integral of dy by dx with respect to x. That should look familiar. That's the kind of thing we dealt with when we looked at parametric area. We had dy and we didn't want it, so we turn it into dy by dt multiplied by dt, that kind of thing. Well, in this case we can do a similar thing. You could think of that integral as being the integral of dy. It's just reversing the process that we did when we had t's and x's and y's. So that integral on the left is the same as the integral of dy, or the integral of 1 with respect to y, if you like. And if you integrate 1 with respect to y, you get y. So it works the same way that we would expect, but you can think of it in terms of integrating with respect to x. And on the right hand side, x squared, we use the ordinary power rules. 2 to the x, we can remember what 2 to the x differentiates to. It'll give you 2 to the x multiplied by ln2, the adjustment factor that comes in because it's not e to the something. So if we're integrating, we'll just divide by that adjustment factor, the ln2. With sine integrates to negative cos. We'll keep the 3x, but it's a linear term, so it doesn't cause us any problems. We just divide by its derivative. And of course at the end you put plus c, the constant of integration. So you'll find with differential equations, just like with any integration problem, there will be a constant of integration, an arbitrary constant, because your differential equation doesn't just represent one single connection between x and y, it represents an entire family of them. So generally speaking, if you can write a differential equation in the form dy by dx equals some combination of x terms, then we can solve by integrating both sides with respect to x, which is equivalent to turning dy by dx into y and integrating the right hand side. Now the first thing you should notice about this is that what we've ended up with is itself an equation. The solution to a differential equation is itself an equation. It's just not a differential equation. It's an equation that has x's and y's, but it doesn't have any dy by dx's or any derivative terms. Okay, next we're going to have an example. You'll see how this is a bit different to the previous one. We're going to start by developing a simplistic mathematical model, and this is a model that you will see a lot of. This is a population model, and many things grow in a very similar way. So there'll be more questions like this, especially when we get into the modeling with differential equations section. A population of 100 rabbits may grow by 20 rabbits in a year. This happened in Western Australia a few hundred years ago. Somebody brought a couple of dozen rabbits across and released them into the wild, and because they had no natural predators and millions of square miles to roam free, they grew at a rate of 20% per year. Well, 100 rabbits turning into 120 doesn't seem like a particularly big growth, but when you have 1,000 rabbits, every year they're now growing by 200 rabbits per year. So the key thing that determines the growth rate is the number of rabbits you have. In other words, the rate of growth, the number of rabbits you get per year, depends on, and in this case is directly proportional to, the size of the population. If you have a bigger population, it grows faster. We can model this proportional growth with a differential equation. dy by dx is the rate of change of y with respect to x. So if we treat y as the number of rabbits and x as the number of years that go by, dy by dx is the rate of growth, the growth rate of the population of rabbits, the rate at which the population grows with respect to time, or per year. And that's equal to 20% of the current population of rabbits. Now I'm going to stick with dy by dx for now, so we don't get confused by having to keep track of different variables. But it's worth noticing that often when we have a population growth question and we have a rate of growth with respect to time, we'll usually use more sensible looking variables for that. So you'll need to get comfortable dealing with things other than just y and x. Now we have a problem here because the right hand side is a function of y instead of a function of x. We can't just integrate with respect to x because we have something involving y. This is where the method called separation of variables comes in handy. This is the main method for this topic. This is the way we're going to deal with differential equations, and if you get a differential equation in an exam, it's almost certainly going to be this type rather than the previous type. The previous type is essentially integration directly. This type is where you have to rearrange things and integrate with respect to x, and as we're going to see in a moment, with respect to y as well. So here our differential equation has got a y term, and on the left, if you look closely, there is a dy term. So we're going to divide both sides by y so that the y term ends up on the same side as the dy term. This might seem like a strange move, but you're going to see what happens next when we integrate things. Essentially, what we're doing here is trying to make it so that dy is a factor of the left-hand side, because when we integrate, we have the integral of something multiplied by dy or dx. If we integrate with respect to x now, we'll get a similar cancelling out to what we had before. If you look closely, the dx and the dx here can cancel out. So 1 over y dy by dx becomes 1 over y dy. And that's going to be the same as 0.2 integrated with respect to x. So now on the left-hand side, we have an integral which involves y, and on the right-hand side we have an integral which involves x. Well, technically it's just 0.2. We could integrate that with respect to whatever we like, but because we have a dx, we're going to integrate it with respect to x. On the left we have 1 over y, and we're going to integrate it with respect to y, so we get ln y. And on the right we just have a constant, so we'll get the constant multiplied by x. And then we have a plus c. The final step here is usually to write the solution equation, because remember the solution to a differential equation is itself an equation, just one that has no dy by dx's in it anymore. We usually write that, if possible, in the form y equals some function of x. And in this case, that works out quite nicely because we can do e to the power of both sides. That cancels out the ln y, and it gives us e to the power of 0.2x plus c. Now, usually, we rewrite that again. So it's worth noticing, because it's e to the power of something plus something, you can break it into e to the power of 0.2x multiplied by e to the power of c. But c is just an arbitrary constant. It's a number, we don't know what it is, and it will change depending on the situation. In this case, c actually corresponds to the initial population of rabbits. If you release 24 rabbits into the wild in Australia, then e to the power of c will be 24. So c corresponds to the initial conditions. In this case, it's actually e to the c that tells you the actual initial number of rabbits. And you can see that more clearly by looking at the alternative version, a times e to the 0.2x. So the number of rabbits can be calculated for any given number of years by doing the initial number of rabbits, which is capital A, multiplied by e to the power of 0.2 times the number of years that have gone by. Okay, now we're going to go through another example. This time I'm going to give you a bit of a shortcut. When we deal with the separation of variables, although technically what I'm going to show you is not exactly what goes on mathematically, that's what we saw on the previous slide, this is a nice way to view it and to rewrite it so that it becomes a little quicker and slicker when you're doing your own questions. The first thing to look at is, do I have a function of x and a function of y that can be separated through only multiplying and dividing? It's got to be through multiplying and dividing because we need to have dx as a factor on the right hand side and dy as a factor on the left hand side. In this case, yeah, it's written as a nice fraction. We could multiply by y squared and y would end up on the side with the dy. And then the function of x that's left over, well, that can end up on the right hand side, and we'll see how the dx appears there. All that we've done is multiplied by y squared and essentially multiplied by dx. Now that's not really something that we can do. Essentially what's happening is we have a dx cancelling with a dy by dx on the left. But to all intents and purposes, this is exactly what happens. And then all we need to add is an integral sign. We don't need to think of this as integrating with respect to x and cancelling things out like we did before. We can just say, move everything involving y to the left, move everything involving x to the right, through only multiplying and dividing stages, and then put an integral sign in front of both the left-hand side and the right-hand side. And straight away we have an integral which involves y on the left, and an integral which involves x on the right. And then we integrate. On the left, y squared becomes y cubed over 3, and on the right, 3 cos x becomes 3 sin x. Cos integrates to positive sin x. And then we have a plus c. Now you might be wondering why we only have c on the right hand side instead of on the left. There's no good reason why we shouldn't have an arbitrary constant on the left, or indeed on both sides. But if we had y cubed over 3 plus a equals 3 sin x plus b, let's say, you could subtract a from both sides and you'd have y cubed over 3 equals 3 sin x plus b minus a. And since we don't know or care what b is and what a is, we would probably just rename that as c. And that's all that's happening here. We don't gain new information by having two different arbitrary constants. So we choose one side and we put it there. The next thing to do, like we were saying before, is to try, if possible, to rearrange in the form y equals something. And if in the process you end up overcomplicating the constant term, then if you're careful, you can replace it with something else. E to the c got replaced with a on a previous example, and in this case 3c is being replaced with k. You'll notice this means the arbitrary constant does not always represent just a straightforward vertical translation. In this case it's something more complicated because it gets factored in before the cube rooting happens. And in the previous example it was a multiplied by e to the power of 0.2x, which means changing the arbitrary constant changes the initial height of your exponential growth graph. Okay, next we're going to try an example from the book. I think this is page 324, and we're going to use this to make sense of the idea of a general solution and a particular solution. So firstly, the key idea. The general solution is what we've ended up with on the previous two slides, where we have a plus c of some sort. So there's an arbitrary constant involved at the end. A particular solution requires you to have additional information. Just like when you integrate something in order to find the curve which has a particular gradient, you'll have an arbitrary constant because there's an entire family of curves that have that same gradient function. Well, in this case, there's an entire family of equations that satisfy the differential equation that you're given. And it's only by telling you the coordinates of a point on the curve that you can pinpoint exactly which curve is relevant to this particular question. We'll work through it and it will make more sense. The first thing to notice is that we have y plus xy on the right hand side. And it doesn't look like it's immediately obvious how we can separate the variables through multiplication and division. But it turns out if you do the logical thing, factorize, then you can suddenly see how the function of y, which in this case is just y, is a factor of the right hand side, and we can divide the entire right hand side by y. At the same time, we're going to divide the left hand side by x squared, so that we can divide the right hand side by x squared. We'll end up with a function of x on the right, and anything involving y will be on the left. And we also multiply by dx. And then we write integral signs in front, and in one quick step, we've generated the integral form of the differential equation. This is what we can actually work out. So the integral that happens on the left is a quick one to do. And it might be that you decide to integrate that one and leave the other one alone for now. It might be that the other one takes a few more steps. I would encourage you not to abandon one side and just work with the other one and not even write it down, because you'll end up losing track of what your equation is. This would be like working with an expression from the right hand side of an equation and forgetting that you've got a left hand side kicking around. So keep them both there and keep the equal sign between them, but feel free to integrate one side while you're still rearranging the other side. Although this may look like one of those awkward fraction problems, it's not that awkward. The term on the bottom is a single term. We can divide through by x squared. 1 over x squared is best written as x to the minus 2 because it's going to use power rules. And x over x squared is 1 over x, and it's best written as 1 over x because then you'll remember it involves logs. As we did before, we'll have a plus c at the end, and it doesn't matter which side we put it on, so we'll leave it on the right hand side in this case. It asks specifically for a solution in the form y equals something in terms of x, so we need to deal with the lmy. We're going to do that by raising e to the power of both sides. Now if you look closely, apart from changing x to the minus 1 into 1 over x, I've deliberately written this out in full, e to the power of every single thing that I had on the line before. That's because it's really easy to make mistakes with powers. We don't want to be writing e to the minus 1 over x plus e to the ln x plus e to the c, because that's not the same as what I've written here. The laws of indices need to come into play, and because we have powers that have been added together, that corresponds to terms which have been multiplied. E to the minus 1 over x multiplied by e to the ln x multiplied by e to the c. Those three terms all multiplied simplified down. I've replaced e to the c with a, because c was just a random number I didn't know, so I might as well think of a as being a different random number that I don't know. E to the ln x is of course just x, and then I've got the e to the minus 1 over x term there as well. So that's now in quite a nice format, and that is known as the general solution. It doesn't have a plus c, but it does have an arbitrary constant in it somewhere. It happens to be something which is multiplied by. Now the particular solution, like we said, requires the boundary conditions. Boundary conditions just mean additional information that tells you about it. Sometimes they're initial conditions in the sense that we know how many rabbits there are at year 0, for instance, but it doesn't really matter exactly what information they give you as long as you have some information about x and y and you can substitute it in. If we replace x with minus 1 and y with e to the 4, either in this final form or potentially in any of the earlier versions, we can still calculate the value of either c or a depending on what we have. And once we've got that value, we can go back to the general solution and rewrite it with our known value for a. So subbing that in and taking care to simplify carefully, e to the 4 is minus ae. Notice we're not going to cancel the e's, we don't get 4 equals minus a, we're going to divide through by e. So on the left we get e cubed and on the right we get negative a. And then we can also change the sign of both sides or divide by negative 1 and get a equals negative e cubed. There are a few ways to write your final answer here. I'd recommend you start by writing it out exactly as it's written in its form here in the general solution, but simply replacing a with minus e cubed. Then, if you want to do any more rearranging or simplifying, we've got two expressions here which involve e. So perhaps, since they're multiplied, we could just add their powers. 3 added to minus 1 over x. That might be a slightly nicer way of writing it, and I believe the book solution is similar to that. They might have 3x minus 1 all over x, or something like that. And this is what we call the particular solution. So this corresponds to the particular curve which was being described in the question. When they said that y equals e to the 4 when x equals minus 1, they were telling us there is a particular curve that I'm interested in. So it not only satisfies the differential equation, but it also satisfies these conditions. And by putting that in, we've managed to find an equation which represents our curve. But this particular equation, there is only one curve that this looks like. There are no arbitrary constants, there are no unknowns in there. This is something you could type into a graphical calculator or GeoGebra and it would graph it for you and you could see what it looked like. It's going to be a slightly weird graph, but you could then verify potentially that if you multiply x squared by the gradient, you get y plus xy.